minimal operator. Wait a second. This part doesn't seem quite like in these directions, but I hope that I will show you the connection at the end. Minimal operator. What was a minimal operator? Is operating in the polynomial shape that kills everything, right? So so here's this very interesting way. These, in the development of the book, I don't know if you look at the end of the book, and there is this determinant and the trace map at the end of the book, and they never talk about determinant at all. And in the preface of this book, they actually brag about this one. They developed this entire thing without determinant theory at all. So here's one. These ideas usually introduced through the determinant algebra, and here's a nice trick they're showing that they pull out something that without determinant. So let's say this is just still local. We're looking at, I don't know if this is going to be the entire vector space or not. We just looked at the eigenvectors and did our best to pull out this nice direct sum of indecomposable spaces. But we don't know if that's going to be equal to R, the V. In the homework, we just tried a dimension. It was the full dimension, so it happened, right? So the rest of the part is kind of outlined to kind of close that up. So if I have this basis like V is a span of V1, let's say it's Vn. And I'm going to find an operator for each of the V1 and Vn, and if there's some common part, and that's going to be the minimal existence of operator. Once you have the polynomial operator exists that kills everything, then there must be a minimal operator because its degree is integer situation. So here's interesting thing. So you have a V1, and you apply that minimal operator of T. So about this. And they apply this T of V1. That's going to be a vector, right? And they do one more, T squared of V1. I don't know. It's not easy. This idea, it doesn't come too easy, but it's not, if you think about it, it's not something that's very difficult to discover if you have time and money to sit down and think about this type of thing. But it goes all the way. The book shows like this. All right, what if I reach the T to the N in V1? Something interesting happens. These are potentially distinct n plus 1 vectors, right? But maybe not distinct. But we're looking at n plus 1 vector listed, potentially different, some of the repeats. When you look at n plus 1 vectors, what comes to your mind? Where V is generated by n, let's say that was a basis. What conclusion do you have? Dependency, exactly. The dependency. If you're looking at n plus 1 vectors in the n dimension, you know they are dependent, right? So some of the, so why don't we go down to the minimal number of this thing? We know it's dependent, right? So go down to a minimal number. You don't have to go all the way up to n. You reach until you have some minimal number of vectors. So find, well, let's just write that down. First. So there's A1, V1, A2, maybe A0 is better. A1, T1, V1, T to the first, and A2, T applied 2 times all the way up to AN, and applied n times V1, right? This is supposed to be 0, and some of this coefficient is non-zero, right? Otherwise, this is going to be independent. If it is dependent, there is this combination where some AK is non-zero. That's the definition of linear dependence. All right, you start from the right, and maybe if this is 0, then you don't have to look at the end, whatever that the highest coefficient from the right. And then we have a polynomial expressions. So we have some polynomial, go all the way up to am and tm v1 equals 0, where am is first non-zero from the right. Then this expression is a polynomial. The leading coefficient is non-zero. It's a polynomial expression. All right? Then I'm going to write the polynomial expression like this. am tm am minus 1 and tm minus 1 all the way down to a0 a1 t of v1 t and a0. That's just the operator, works on exactly the same vector all the time, v1. And that is equal to 0. So we don't know if this is minimal or not, but there is a polynomial that hits v1 and it's going to kill it, right? Is that right? Yeah. So if you have a polynomial, what can you do about the polynomial, especially over the complex number? So I have to assume there's a complex number. Is all over the complex scalar. Everything gets easier. Let me remind you of this theorem, fundamental theorem of algebra. What was it? If you have a polynomial of a complex coefficient and it factors completely to the linear factors, right? That's one at a time. It has complex roots, so you factor on one complex root, t minus alpha. And again, it's a complex coefficient. You factor on one at a time. So this actually factors into am over t minus, let's say, alpha 1 I. If you substitute capital T with a little t, then it's a polynomial, and polynomial factors, and this factorization, if you expand this polynomial operator, you get this one exactly back. It's logic. And maybe it repeated a couple times, so I'm going to write it S1 to collect them all. So alpha 2 is necessarily distinct, and collect S2 like that, and it ends it with whatever the last one. I'm going to call alpha, I'm running out of letter here, C, and I, and SC, like that is V1 equals 0. All right? So that kills it. And that was the business about V1, but nothing special about V1, right? You do V2 as well, V3 as well. So for V2, you're going to have another set of this one, right? Like that. That's going to be beta maybe? Beta 1 of, STU1 and things like that. Make sense? And you do all the way up to Vn, right? And we have all these factors there. Then what is going to be the, an operator that kills everything? So suppose you have this factor raised to S1, this factor raised to S1, and everything has this expression. How are you going to choose some operator here such that it kills everything, Vk, no matter what the k is? Combination of all that, right? So how are we going to choose? If that appears here, the S1, maybe it appears in here, right? Then you're going to choose higher power or lower power. You have to make sure that this gets killed, so you're going to choose higher power, right? What is that called? Greatest common divisor of a polynomial. If you look at it as kind of integer factorization. So the greatest common divisor of all these factors appearing in here. Actually, I was wrong. It's not a greatest common divisor. Choosing the highest one is called least common multiple, right? Greatest common divisor is getting smaller and smaller. It's the least common multiple. That's what it is. Think about 2 to the 3rd, 3 to the 5th, and 7 to the 1st. And the second one was a 2 to the 2nd, and 3 to the 7, and 7 to the 5th. We want to make sure that it kills everything. So, if I just have this one, if I have 2 to the 3rd, and I can separate that 2, and you can kill it with a 2 to the 2nd, the other one. So we have to choose the largest power. If you collect the largest power, 2 to the 3rd, 3 to the 7 is the largest power, 7 to the 5th is the largest power. What is this term relative to the other two? Is the least common multiple of these two things. Okay? So choose all the highest power. So it's the least common multiple of everything that appeared in here if you plug in vk, and that's always 0 for all k, 1 through n. So this polynomial is made out of this choices and out of there, so it doesn't involve any k. It's just a collection of that one. So that is a polynomial operator that annihilates, kills the whole v. v1 and v2, v3, they're all killed. Therefore, all the linear combination is called this linear operator. All right? So once you have a polynomial operator, you can think about the smallest degree that kills it, right? Smallest degree that kills it. Then you can think about those indecomposable spaces in there and what it kills, W1, and think of it like that. So from there exists a minimal operator. Of T on B. So let's say that minimal operator is what I use Q T. So that looks like. I hope you understand this leading coefficient AM doesn't really affect if it's going to kill it or not. You can just divide everything by the leading coefficient. So when we consider minimal operator, we usually consider monic minimal operator, T to the M plus AM minus 1, T to the M minus 1, like that. A1T plus A0 identity operator there. This is the smallest degree that's going to kill everything. All right? But it still has factorization because it's a polynomial. So it's going to have really now T minus lambda 1. I'm going to begin to use lambda now because this is related to the eigenvectors. So here I think I used LK, L1 in there. T2 lambda 2. These are all distinct values, lambda L2. Go all the way up to T minus lambda M. That's not the same M, so I have to use a different. Let me use this capital M, since I have to be consistent. Capital M here, capital M minus 1, capital M minus 1. It's a little m, and here's LM, like that. So it factors like this, where L, lambda 1 through lambda m are all distinct complex number, and they're repeats like that. And next theorem is relating to this one, that you can think about, these are the operator kills everything, right? And you can think about what is going to kill by this guy, what is going to be killed by that guy. And those are exactly the minimal operator for individual the bits and pieces in here. Remember those homework solution number 3? They all look like that, right? T plus 4i raised to the power. It is about that indecomposable block. So the minimal polynomial picks up those blocks in the correct size. So that if you have that the right matrix there, and you can write down the minimal operator easily like that. We just looked at the matrix that involves only one factor in there. If it is combined, it's going to look like this. But discovering that it is actually have to be in that form is a lot of work. But if you write down that matrix, convincing yourself this is going to be the minimum operator is not that hard. All right? So there is a structure there, and the final statement is in the most general form that you can relate it back in here and see the picture and how it's come about. It's a 3, and here's number 4. This is the statement. Let V, everything is in a complex, so I'm not going to state it here. So here's the statement: is let v1, v21, vm1. Not only they're linearly independent, this is a maximal set of eigenvectors that are linearly independent. This is what that means. A set of eigenvectors that are linearly independent makes perfect sense, right? You know what that means. What do I mean by maximal? If it is this one, if there is one more eigenvector outside of the span of this one, then you can make it bigger, linearly independent, right? Outside the span means linearly independent. So you can't do that anymore. There's span of this one, and outside the span of this one, there's no more eigenvectors. But it's not unique. You can choose a different set of eigenvectors. But the size is unique. And that's a dimension theory. You cannot have one time 3 maximal set of eigenvectors, and next time for the same t, get a 5 different set of eigenvectors. That doesn't work if you think about a dimension theory. So we have that, and what happens is that, and then we have not then, what is the right statement? Let W1, Wm be the indecomposable subspaces constructed constructed in the number 1, right? As earlier, by pulling it back of each of these linearly independent, and these are all direct sum, right? The final statement is that then actually V, the entire thing, is W1 all the way to Wm. Okay, we looked at all the maximal size of the eigenvectors that are linearly independent. For each of them, you pull back using that mechanism, and you have all these things. And the earlier result, they're direct sum, and this one says actually the direct sum is the whole thing. Everything falls into this thing. All right. And another thing, and then here is a WK has the matrix of the form lambda k. They're all the same. For the WK, there's all same diagonal elements. And above it, it's all 1, 1 because it's generated by pulling it back. So this is all invariant, indecomposable, and these matrix, the matrix of each of the thing is given by this block. So the matrix of entire V is made out of this block, right? Here's an example. So that's the end of the theorem. And the theorem says, compute the maximal set of eigenvectors, linearly independent, pulling it back, and their direct sum is the entire decomposition. As an example, by doing that, you end up at this matrix, 2, 1, and 3 down there. What is the size? Is that 5 by 5? Everywhere else was a 0. By doing that boring calculation with using echelon form, you arrive at here, right? And you guarantee that. That's what this theorem says. So think about the minimal operator. Minimal operator. All right. You want to kill that guy, right? So how do you kill that guy? By what operator? T minus 2 to I. That's going to kill that one. And that's not going to kill that one, T minus 2, 1. But if you square it, that's going to kill that one, right? So about T, next one is T minus 3I. That's going to kill that one, right? So this one kills that, and that one kills these 2, 3 blocks. Killed everything. So this is going to kill everything. All right? So if you plug in E1 and E2, you can swap this around. Usually the operators don't commute each other, but if it is made out of one variable, one t like that, you can easily swap each other because you can expand it. They all end up in the same thing. So you can show this is actually annihilates everything. The minimality, it gets tricky. If you just play with this one, then you can show that any powers, these are the minimal powers. But maybe out there, there's a degree 2 that is not looking like this, completely different, but it still kills it. Who knows, right? That's the tricky part. And here, whatever that is, it factors still like this. And difficult part is that polynomial factors uniquely. Did you hear about that? I don't know what theorem that is. Polynomial factors uniquely any field, but an over complex field factors uniquely is a part of fundamental theorem of algebra. You can't change the set of zeros. Set of zeros are unique, and multiplicity is unique. That is not just coming from the set of zeros, so that's a different part. So polynomials factors uniquely, but polynomial operators do not factor uniquely. Think about it. If you want to compare this operator with the other operator, you have a tendency to matching these factors. Therefore, this is it. But I'm saying is that polynomial operator does not factor uniquely. You can't just comparing by this factors and that factor. But polynomial itself does factor uniquely. So that's a tricky part of establishing this thing I wrote down here is really the minimal operator. But if you stick to this factor, it's easy to see the minimal exponents. That's the easy part. All right? So I have one more statement, but that's probably have to wait next time. But this is, hopefully, you see this as a diagonalization because each of that, I'm going to call that, what did I call this one here? Semi-diagonal block. That's what I said, right? Semi-diagonal block. So how is this for matrix for V? The entire V is going to look like this. I'm going to call this A1 and A2 and all AM in there. The entire matrix is going to look like this, but each of A1 through AM is the semi-diagonal block. So whole thing is really the semi-diagonal combination of semi-diagonal block. In particular, is upper triangular, which is the main conclusion that section, chapter 5 or 6 draws. And then I formulate it in this way. All right? All right, it's hard, but